Hello, today we will introduce the famous Cramér-Rao inequality. This is a fundamental result in estimation theory, and in particular we will show how geometry makes the result intuitive. It is a statistics analog to the famous uncertainty principle in quantum mechanics, as it reveals the intrinsic uncertainties in unbiased estimators. So let me know in the comment if you wish to see more videos on estimation theory, and if you have seen this visualization of the Cramér-Rao inequality before. So without further ado, let's get into the main topic. As usual, let's begin with a motivating problem. Estimate the parameter lambda in a Poisson distribution. So suppose we have a random sample, x1 all the way to xn, that are IID and each follows the Poisson distribution with parameter lambda. Our goal is to estimate lambda from the random sample. We first recall for a Poisson distribution with parameter lambda, its mean and variance are equal. They're both lambda. So we can consider using the sample mean x bar or using the sample variance big sigma squared as an estimator for lambda. So immediately this raises the question, which estimator is better and according to what criteria? It can be shown that both x bar and big sigma squared have mean lambda, which we will do right now. From an earlier video, linked in the right corner, we show that if the expected value of xi is mu and the variance of xi is sigma squared, assuming that xi's are IID, then the sample mean has an expectation of mu and variance of sigma squared over n. And this leads to the second moment of x bar, mu squared plus sigma squared over n. And to calculate the mean of the sample variance, we first use an identity and write big sigma squared as 1 over n minus 1 times the sum of xi squared minus n over n minus 1 x bar squared. And then take the expectation. Simplifying gives sigma squared. So for IID Poisson distribution, since sigma squared is lambda, the sample mean and the sample variance have the same expectation, which is the parameter we wish to estimate. And for that, we call them unbiased estimators. For this example, as far as bias or the lack thereof is concerned, x bar and sigma squared are equally superior. So we need some other criteria to evaluate their performances. Our gut feeling tells us because big sigma squared involves xi squared, and squaring things tends to inflate variability. So it feels intuitive that the sample variance is less accurate. But we have to actually calculate that. And the most important question is, what would be an optimal unbiased estimator? And do such things even exist? The Cramér-Rao lower bound is for answering such questions. We now give the formal definition of estimators. Suppose we have a random sample, scripted x equals x1 all the way to xn, which follows a probability distribution p theta, where theta is the parameter. We assume theta is fixed but unknown. And the range for all possible values of theta is denoted as big theta. We call that the parameter space. Our goal is to estimate a function g of theta, where g is a given function, and we assume that g is smooth. An estimator t is a function of the random sample scripted x only, and t cannot depend on theta. For example, the sample mean and sample variance are both estimators. The requirement, t cannot depend on theta, is to prevent cheating, in which case we can just pick g theta itself as its estimator, which is absurd. And note that in the definition of estimator, we say nothing about our target g theta. Let's look at a visualization of this formal definition, and in particular, the meaning of theta independence. First, we have our sample space, Rn, the possible values of the random sample. The parameter space, big theta, which we visualize as an open interval. Next, the range of g. Recall that g is a function of theta. The estimator t maps the sample space into the range of g. The requirement of parameter independence in the definition of estimator says t is the same function for all theta in big theta. If t were allowed to depend on theta, we would end up having a family of functions t theta parameterized by theta, and that's not what we want. Note that in our setup, there are actually two functions that takes the parameter as an input. The distribution of the sample also depends on theta. And let's visualize distribution p theta as a family of contours. You can think of this as the density contour. So imagine we have a value, theta1, in the parameter space. its corresponding distribution p theta 1 is as such. So under this distribution, the random samples are more likely to occur in this region. If we change the parameter value to theta 2, the distribution changes. So now the random samples are more likely to be observed in this region. And g of theta 2 might also differ from g of theta 1. But while this is happening, that is changing the value of theta from theta 1 to theta 2, t remains the same function. If x is observed, tx is the same, regardless of the value of theta. And so now we will define the unbiased estimators. Let t be an estimator, and we assume that g has finite second moment for all values of theta. Here, the expectation operator is denoted as e theta, because taking expectation depends on the distribution, and the distribution is parameterized by theta. T is called an unbiased estimator of g of theta if the expectation of t equals g of theta for all theta. And now we introduce our optimality criteria. Basically, we wish to make the variance of an unbiased estimator as small as possible. An estimator t star is called a uniformly minimum variance unbiased estimator, aka UMVUE, of g of theta, if for any unbiased estimator t of g of theta, the variance of t is always greater or equal to the variance of t star for all theta. By uniformly minimum, we mean the quantifier for all theta. So that's the formal definition. Let's visualize it using the geometry of random variables. In an earlier video, link in the right corner, we introduced the mean and variance right triangle. Basically, for any random variable with finite second moment, its mean e of x is the orthogonal projection onto the subspace 1, that is, the span of 1, the set of all constant or degenerate random variables. The perpendicular component, x minus ex, of the projection is known as the residual of x. The squared length of the residual is the variance of x. And in the same video, we introduced the bias variance decomposition in the context of estimation. And as we can see, if the estimator theta hat of theta is unbiased, the shaded right triangle collapses to a line segment. And let's recall the geometry in terms of formulas. We have an inner product in the space L2. The inner product between x and y is the expectation of x times y. And the orthogonal projection of a random variable x onto a non-zero random variable y is the inner product between x and y over the inner product of y and itself times y. For any unbiased estimator t of g of theta, its projection onto the subspace 1 is exactly g of theta. And we define the residual t tilde as t minus g of theta, and this clearly lives in the orthogonal complement of the subspace 1 orthogonal. But we shall demonstrate there is another geometric relation which is far more subtle, and that pretty much immediately gives rise to the Cramér-Rao lower bound. Without loss of generality, let's assume the distribution p theta to be a continuous distribution, with density f of theta parameterized by theta. This way, the unbiasedness condition takes the form of an integral. The integral of t of x times f of x and theta dx is g of theta, where the integral is taken over the sample space, which we omit for convenience. And we're interested in the variance of t. And here comes the key intuition of what follows. We have two competing sensitivities. The sensitivity of g relative to theta versus the sensitivity of f relative to theta. If g is sensitive to theta but f isn't, then variance of t should be large. Let's think about why. Imagine theta only changes a little bit. If g is sensitive to theta, in response, g changes a lot. F, the distribution, isn't sensitive to theta. So by changing theta a little bit, the random sample x shouldn't look too differently. But because t is an unbiased estimator for g, and g just changed a lot, so the expectation of t must change accordingly to match that. So we just established that even though the random sample, the raw input of t doesn't change much, the value of t changes a lot, which means large variance of t. Next up, we have the opposite scenario. If the distribution f is sensitive to theta, but g isn't, this will lead to a small variance in t. Let's think about why. G isn't sensitive to theta in this case, so changing theta by a small amount pretty much does not change g. But the underlying distribution is sensitive to theta. So that means given a small change in theta, the raw random sample should look quite different. But just like in the previous case, t is unbiased, so the average of t follows the trend in G, which is a small change. So even though the observed sample changes wildly, the values of t pretty much does not change, which means a small variance of t. In the first situation, estimating G is intrinsically hard, because two almost identical random samples would lead to wildly different estimates. In contrast, in the second scenario, accurate estimation is easy. Two wildly different samples would lead to almost identical estimates. So that's the intuition. The Cramér-Rao lower bound is nothing but a formal statement. And since we're considering sensitivity relative to theta, let's differentiate with respect to theta on both sides of the equation and see what happens. And here we're going to assume a regularity condition. Differentiation under the integral sign is permitted. And doing so gives the right-hand side of equation 1, the integral of tx times the partial derivative of f with respect to theta dx. And that's g prime of theta. And as we've been seeing so far, to do geometry, we need an inner product. So we want to recast the right-hand side of 1 as an inner product. For that, we use a trick. We multiply and divide the density. But take a look at the expression in the middle. By the chain rule, that's just the partial derivative of the natural log with respect to theta, which we denote as s. And now the right-hand side of equation 1 is an expectation. We can put it as an inner product of t and s. So overall, we have the inner product between t and s is g prime. S is called the score, and it measures the sensitivity of the distribution relative to theta. So in this inner product relation we just derived, on the right-hand side we have g prime, the sensitivity of the target relative to the parameter. And on the left-hand side we have the sensitivity of the distribution. T remains unbiased, and that's the relation that links the three. And by the way, I recommend going back to this diagram when you retrace the argument of the sensitivity of the target versus the sensitivity of the distribution relative to the parameter. And let's now focus our attention on the score. The first property is that S has zero mean for all theta. And geometrically, that means S is orthogonal to 1. And the proof is straightforward. Just use the formula for expectation. The density F cancels. And then we interchange the order of differentiation and integral. Once again, we're assuming regularity conditions hold. But now the integral is just the integral of the density, which is always 1. So we have d over d theta of 1, which is of course 0. So now we have two vectors t tilde and s living in the orthogonal complement of 1. And here's the proof. We just showed earlier that g prime of theta is the inner product of t and s. We can write t as t tilde plus g theta, and then expand using the bilinearity of the inner product. So we have t tilde and s inner product plus g of theta times 1 and s inner product. 1 and s inner product is 0, which finishes the proof. Next, we define the Fisher information I of theta. This is simply the squared length of the vector s. And now we can apply the Cauchy-Schwarz inequality. The absolute value of the inner product of s tilde and s is less than or equal to the product of the length of t tilde and the length of s. The left-hand side of the inequality is the absolute value of g prime of theta. On the right-hand side, the length of t tilde is the square root of the variance of t, and the length of s by definition is the square root of I theta. Rearranging, we get the variance of t is greater or equal to g prime of theta quantity squared over I of theta. And that's exactly the Cramér-Rao lower bound, CRLB. It's a ratio between the sensitivity of the target against the sensitivity of the distribution. And this reflects our intuition. The variances of unbiased estimators are controlled by the competition between these two types of sensitivity. Recall, what the Cauchy-Schwarz inequality says is essentially the cosine absolute value is less than or equal to 1. By rearranging the Cauchy-Schwarz inequality, we get t length greater or equal to the absolute value of the inner product of t tilde and s over the length of s. This right-hand side is the length of the projection of t tilde onto s. So now the CRLB itself has a geometric meaning. The square length of the projection of t tilde onto the s direction. The same for all t. So here we can add the square root of CRLB onto the diagram. The CR inequality is now obvious. And of course, equality holds when t tilde and s are parallel. Or equivalently, s is a scalar multiple of t minus g of theta, where the proportionality constant a may potentially depend on theta. 2 remarks on CRLB. The CRLB is not always attainable, even when the regularity condition 1 holds. Recall the regularity condition 1 allows for interchanging the integral and derivative. If the regularity condition 1 fails, the expression given by the CRLB might be greater than the actual variance of the UMVUE. So in the first remark, the CRLB is not sharp, and in the second remark, the CRLB is useless. Let me know if you guys are interested in seeing those situations. And now let's go back to the motivation problem and apply what we just learned. Suppose x1 all the way to xn are IID each Poisson lambda. We can easily write down their joint probability mass function. By independence, this is just the product of the marginal PMFs, and simplifying gives the right-hand side. And then we calculate the score, taking the natural log of f, and then differentiate with respect to lambda partially. Simplifies to minus n plus 1 over lambda times the sum of xi. And s can be rewritten into n over lambda times x bar minus lambda. And this is exactly the condition for attaining the CRLB. Therefore, we conclude x bar attains the CRLB and is a UMVUE of lambda. Let's check that independently. We're going to actually evaluate the CRLB, g prime of lambda quantity squared over I of lambda. Here, because we're just estimating lambda, so g is the identity function. So g prime is 1. And now we calculate I. I, by definition, is the expected value of s squared. Since s has 0 mean, as always, so this is just the variance of s. So we're calculating the variance of minus n plus 1 over lambda times the sum of xi, which simplifies to n over lambda. Because xi's are IID Poisson, the variance of xi's are just lambda. So indeed, the variance of x bar attains the CRLB. But what about the sample variance? The sample variance big sigma squared is quadratic in xi. But we just saw that s is linear in xi. Therefore, the sample variance minus lambda cannot be proportional to s. The CRLB cannot be attained by big sigma squared. And in this case, we can actually calculate the variance of s squared using this formula. For more details on this formula, you can go to the book by Casella and Berger, which I made a review a few weeks ago. So the variance of s squared is given by 1 over n times theta 4 minus m minus 3 quantity over m minus 1 quantity times theta 2 squared quantity, where theta 2 and theta 4 are the second and the fourth centered moments of xi. For Poisson lambda, theta 2 and theta 4 are given as lambda and lambda plus 3 lambda squared, respectively. The calculation details for theta 2 and theta 4 are given in the appendix. The variance of s squared turns out to be lambda over n plus 2 lambda squared over m minus 1. The first term is the CRLB. Isn't all of that beautiful? As promised, this is the appendix, the centered moments of Poisson lambda. We wish to calculate the expectation of x minus lambda to the n for x follows a Poisson distribution. And the idea is to use moment generating function, or MGF. The MGF has this general property. Assuming regularity conditions hold, expanding the MGF into a power series, the moments can be attained from the coefficients of the expansion. The Poisson distribution has a well-known MGF, the exponential of lambda times e to the t minus 1 quantity. From this, we can easily derive the MGF of x minus lambda, factoring out e to the minus lambda t, and now we're just going to use a computer algebra system to expand this function as a power series, and we just need the second and fourth order terms. And that's it for today's video. If you enjoyed the video, please consider like and subscribe. Thank you very much for watching, and I'll see you next time. Bye.